Alright, for our last video for week 6, we're going to talk about regression. This video is going to follow up on that last video where we talked about describing linear relationships and the correlation coefficient. If our paired data, x and y, is approximately linear, we can build a model called a line of best fit to model that relationship between x and y. The line of best fit minimizes the difference between the actual y values that we measured and the y values that are predicted by the equation. The difference between the actual y and the predicted y is something called a residual. So a residual is actual y minus predicted y. And you'll notice we're using y with a little hat called y hat creatively to represent the predicted value from our equation. So what we're doing is we're minimizing the residuals. And the equation that overall creates the minimum residuals is our line of best fit. The process that we use to minimize the residuals and the line produced by that process is called the least squares regression line. So we are finding the regression of one variable on another. And the equation that we get our least squares regression line is y hat equals ax plus b. And you'll notice that looks kind of like y equals mx plus b. That looks like our slope-intercept form. Y hat is the predicted y value for any given input x value. A is the slope of our least squares regression model. X is our independent variable. And b is our y-intercept. So this is functionally slope-intercept form with slightly different notation to accommodate the fact that we're doing statistics and not algebra. To find the least squares regression line, we're using technology. Much like the correlation coefficient, we can do this by hand. There is a formula for this. I think the book actually outlines it for you. But I would not encourage that unless you really enjoy tedious calculations. On your calculator, to get the equation for the least squares regression line on a TI, it's actually the same process that we went through to get the correlation coefficient. Put the values in list 1 and list 2, call linreg ax plus b. When you run it, the very first two values that come out are a and b, the slope and y-intercept of your linear regression equation. For GeoGebra, the first two steps are the same. Put your points in a list, press enter. But instead of calling correlation coefficient, you're going to call the function fit line. Very creatively named because we're making a line of best fit. So fit line and then the name of your list. So we're going to go ahead and do two examples using the same data that we saw from our last video. So we're back with our scuba divers. And this says find the LSRL for the regression of y on x and use it to predict the maximum dive time for a diving depth of 75 feet. Can we use the LSRL to predict the maximum dive time for a diving depth of 120 feet? Why or why not? So we'll go ahead and put our data into a list. Oops. Try again, Mr. J. Oh, how did that happen? Oh, I forgot the 100. That's how that happened. There we go. So data's in a list. I want to create the least squares regression line. So stat calc linreg ax plus b. And you'll notice here it gives me a value for a and a value for b. So when I write that down, my equation is y hat equals, and then a is the thing in front of the x, negative 1.114 x, and then plus whatever my b is. And I can see from my calculator my b is 127.238. So that equation models the data that we saw in a scatter plot. And we saw the scatter plot last time, second stat plot. We can see our stat plot is on. Whoops, that is not what I meant to do there. There we go. We can see our graph for dive depth versus dive time. I'm going to enter in the regular y equals. Ooh, why am I... Hang on a second. I think this is set up for my trig class. Sorry, I had the mode set up for polar coordinates from my trigonometry class in the spring. So this is just y equals, and this is my function menu, and I'm just going to type that equation that we just wrote down. Negative 1.114, and then the variable button, plus 127.238. And then I'm going to go back to zoom stat, and you can see my line of best fit in orange. And you'll notice 1 point's almost on the line, and then I've got 2 points that are above it and 3 points that are below it. And you'll notice this vertical height here and here is bigger than these little itty bitty vertical heights here. And so those vertical heights that are higher versus those vertical distances that are lower kind of cancel out, minimizing that overall residual, the vertical distance from the actual values in blue versus the predicted values, which are points on the orange line. We're asked to predict the dive time for a diving depth of 75 feet. So there's two ways to do it. The first is with algebra. They're telling me that my dive depth x equals 75, and I can use my equation and just plug that value in for x. Plug that in my calculator, it should give me a predicted value. The other thing that I can do is second calc, and I go value, and I input an input of 75, and you'll notice it puts me on the line, and it tells me y is 43.688. So I have a suspicion that this is going to be 43.688, but I'm going to check it by going back to our home menu and doing the algebra. And you'll notice that manual calculation gave us the same calculation that the graph did. So we can use algebra to make those predictions by substituting in the given x values to find the predicted y. Or we can use the graph, and from the graph use the calculate function, give the calculator the input, and it will find the output for us. The second part of this question says, can we use the LSRL to predict the maximum dive time for a diving depth of 120 feet, why or why not? And looking at my data, my minimum x value is 50, my maximum x value is 100. And a general rule for statisticians is you should not use least square regression lines to make predictions outside of the actual values that you have for x. And the reason we say that is, yeah, this data in this range looks vaguely linear, but I don't know if I were to graph it, if I have all of these linear points and then I get outside of 100 and all of a sudden it shoots back up, or maybe below 50 it shoots back down and my actual graph is an S shape. Because I only collected data here, I may be getting a linear chunk from a relationship that is not linear for the whole x-axis. So as a statistician, you should not make predictions outside of that range of inputs that you had in your sample data. All right, I'm going to do one more example really quick, and then we will be done with the week 6 material. So our second example, we're using that flu data from our last video. And it says, find the least squares regression line for the regression of y on x. Use it to predict the expected number of flu deaths for a year in which there were 25,000 cases. So we go to our calculator and we enter our values. And then we go stat calc linreg ax plus b. So y hat equals, and then our slope is 0.0017, would round up to 2, so 0.002x, and then our b is negative, so minus 22.820. And I'm going to do what we did last time. So second quit. I'm going to go to my y equals menu, and I'm going to reset that equation to our new equation. 0.002x minus 22.82. And then I'm going to graph my data. And you can see this is the data that we saw for flu cases. We have all of this data here, plus that little weird outlier from the year we were all in lockdown. And then my orange best fit line where some of the data is above and some of the data is below. So a review, I can do this with algebra if I want to make a prediction. I'm told that the number of cases is 25,000. So I can take my equation, and where I see an x, I'm going to replace it with 25,000. Or, oops, I can use the calculate function. So from my calculator, I go second trace, and then I'm going to choose value, and I'm going to enter my input, 25,000. And it spits out an output of 27.18. And I'll do what we did last time. Let's double check with the algebra. And running it manually gives us that same answer. So for a year where there were 25,000 cases of diagnosed flu, we would expect to see about 27 people die from the flu in that year. All right. A side note before we end the video, these two examples, when we found the correlation coefficient in our last video, both of them had correlation coefficients that were 0.9 or higher, meaning both of these classified as fairly strongly linear. If you are looking at a situation where the data is not strongly linear, you probably don't want to use that least squares regression equation to make predictions. So the very first video in week 7, we're going to look at how do we tell when it is safe to use our linear model to make predictions and when is it not safe. And it turns out we can do that using a very specific hypothesis test. All right, if you have any questions on the week 6 material, you can catch me via email or during my office hours from noon to 1 and 7 to 8 on Tuesday or Thursday. Warning, on Wednesday of week 6 I will be traveling, and then again on Monday of week 7 I will be traveling as I need to go to a family member's funeral, and I will be out of town for a few days. So office hours are a great chance to catch me live. Otherwise, email, and keep in mind that Wednesday's not a great day to get a hold of me, as I probably will not have my email open while I'm on the road. I hope you guys have a great rest of your week, and I will see you again for week 7.